Please take your seat so that we can start. Okay, our next speaker is Kreckel, and she will be connecting small-scale physics to galaxy evolution.
Great. Thank you. So when we want to build a multi-phase complete view of galaxies and galaxy evolution, we really need to come at this from a multi-wavelength perspective as well. So we've already seen, of course, these sort of pictures of the matter cycle, but it's also critical in this multi-wavelength, multi-phase view to think about also the connection of scales, right? So we've heard a little bit about this today as well, and how those stars that form feed back energy and matter into their surroundings through radiation and winds in the early phases, but also enriched material in the end phases, especially through supernova explosions. And then all of this material is available also to sort of affect the large-scale evolution of galaxies. So the open questions that I have been interested in studying are focused on which feedback processes are really dominating in this cycle and on what scales. How do the heavy elements or the metals build up within galaxies? And then how does that energy and material cascade from the small to the large scales, or from the large to the small scales perhaps? So a lot of the work that I've been doing is within the context of the FANGS collaboration. There hasn't been a FANGS talk yet, so just as a brief overview, this is a collaboration interested in the interplay of the small-scale physics of gas and star formation with galactic structure and galaxy evolution. This collaboration is large and ever-growing in order to encompass a really multi-wavelength view in our study of nearby galaxies. And so our core sample of galaxies to date has focused on a sample of about 74 galaxies that are selected to be in the south and relatively face on. They're sort of representative star-forming main sequence galaxies that are close enough on sort of less than sort of 20 megaparsec scales that ground-based facilities with 1 arcsecond will be able to achieve something like 50 to 100 parsec resolution and isolate individual star-forming regions. And so we've taken a really multi-wavelength view. Our core data sets are targeting all of these galaxies with ALMA, HST, and now recently JWST. Our core sample of 19 of them had originally been observed with MUSE, which is an optical integral field spectrograph to get optical spectra at each pixel. And over time, we've sort of built up that sample to cover about half of these galaxies. And all of these data sets, we really make a point of making public, right? So we have papers presenting all of these core data sets as well as actual derived data products available on our website. And we're always interested in growing this data sample, so we've also been investing a lot of time in building up other wavelength coverage, FUV from AstroSat, H1 from the VLA and Meerkat, narrowband and dense gas tracers as well. Together, this gives us really a beautiful view of the cold ISM, here traced in JWST, but also through ALMA and other wavelengths that we have, that we can complement to what the stars are doing, here seen in HST, but you also see in pink here all of these massive star-forming regions in order to build up this sort of comprehensive view of these galaxies. And a lot of my work has focused on doing studies that involve the MUSE data. This is an optical integral field spectrograph. Each pixel has a full spectrum, so you can look at emission line features mapped across the disk in order to see all of those massive star-forming regions and quantify their properties, the gas phase metallicity or the ionization source. But we also have stellar continuum emission in order to track the stellar populations that are present within the disk. And we can do this across a representative central star-forming disks of these galaxies, but with enough spatial resolution, if we zoom in, that you can really see how we can resolve these individual star-forming regions from each other. This is a 3-color image combining 3 different optical emission line tracers, so you can see how the different colors are tracing different ionization sources, from the blue-colored here planetary nebulae to the pinkish supernova remnants, and then the sort of yellowish H2 regions. So in this talk, I'm actually not going to focus on the stellar feedback physics, although this is something my group has spent a lot of time in the past years working on. So I just wanted to highlight a few results. We've done a lot of work on linking the star clusters from HST with those nebulae identified in the Mu spectra in order to build up sort of an evolutionary sequence in the H2 regions. We've quantified the links between ionizing star clusters and the winds and supernova energy that are injected into turbulent ionized bubbles, and found that both are necessary to drive that turbulence on these small scales. But when you look at molecular gas superbubbles that are also identified on sort of these 100 parsec scales, it's really supernova explosions that are necessary to drive these large-scale molecular feedback features. And finally, my student just a few weeks ago submitted her first paper to look at all of the supernova remnants mapped out across these disks. So we can really start to put together a lot of pieces of the puzzle of how the feedback physics is interacting with these galaxies to drive their evolution. But in this talk today, I wanted to talk more about the metallicity distribution across the galaxies. So when you look at these galaxies, you can see we are picking out individual star-forming H2 regions that are these sort of photoionized bubbles. These are on relatively small scales within a galaxy, sort of 10 to 100 parsec scales. You can think of them as tracer particles where those massive stars are illuminating the surroundings, so they're embedded in some atomic gas and molecular gas potentially that's all being photoionized by these massive stars. And so from studying these individual H2 regions, we make inferences about the temperature and density structure in order to understand from the optical emission lines that we see what the gas phase chemical abundances are, typically traced through the oxygen abundances. So then if we look at a galaxy like this, where each pixel in this image is from our optical IFU data cube, we have a spectrum at each of these locations. We can pick out morphologically all of the H2 regions and then measure the integrated spectra and make a map of the metal distribution across this entire disk, right? So you can see just immediately sort of the radial metallicity trend. There's higher metallicities in the center compared to the outskirts. And this is really a huge step forward from what had been done before, where these sort of radial trends had been seen with samples of maybe tens of H2 regions to a sample of thousands of H2 regions, where we can start to talk then not just about what's the radial metallicity gradient, but also what's the offset in metallicity for any of these regions from the linear radial trend, which is clearly dominant in all of our galaxies, and what's the global scatter in metallicities that we see, and what's regulating that, and how does that connect to galaxy evolution. So if I go back to this picture of our map of the metallicity distributions, and I fit and subtract off just a linear radial metallicity gradient, then you can see the residuals in that, essentially. So you're seeing then the variations in abundances mapped across the disk. And so your eye is drawn, of course, to a number of patterns in here. So you might see, oh, this spiral arm ridge looks a little redder, looks a little more enriched, maybe, compared to the rest of the disk. I'll come back to that point. But you'll also see that there's many places where you see extended regions where the metallicities appear very homogeneous and on large physical scales. So this is 3 kiloparsecs scales. So you see quite consistently across the disk that use these patches where the metals seem very homogeneous. So to quantify that, we looked at the scatter in the metallicities as a function of physical scale for an initial sample of 8 of our galaxies. And in all of them, we found that the metals are significantly more homogeneous on these sort of small sub-kiloparsec scales in all of these systematically. I'll come back to the offsets between these, but if you remove that and account for that and compare with the null hypothesis where you randomized all of your metallicity measurements across the disk, then you really see that there's this significant increase in homogeneity on these small scales in all of the disks. And in fact, this is getting to the level here, these numbers are very small. If you study our ability to make a metallicity measurements at all, this is basically hitting our uncertainty limits in our line flux measurements, never mind the uncertainties in all of the strong line prescriptions that often get used. Okay? So we see globally this homogeneity also that's increased on these very small scales. I mentioned that we do see some evidence for local signatures of azimuthal variations, so along spiral arms. We see in our sample maybe about half of the galaxies, but have some potential correlations with spiral patterns, although it's often on only one arm and not the other. This has been seen in some other work with larger samples as well. And so in fact, it's an interesting position now where the simulations are starting to predict actually much stronger variations between spiral arms and inner arm regions in terms of the abundance variations that are predicted compared to what we actually observe. So I think there's some interesting cross comparisons to be done to see how well that we're actually reproducing sort of the mixing processes that are happening in the disks in these simulations. Going back to the global homogeneity that we were seeing in our galaxies, so now we are looking at our full sample of 19 galaxies that have these Muse observations. And so you might, so this is the global scatter in metallicities that we've measured, and you might think that the stellar mass is the regulating parameter of all galaxies, and so you might expect to see correlations here. We don't really see any driving correlations here. Also with star formation rate, we don't see any very particularly strong correlations between that homogeneity and the level of star formation happening in the disk. What we do see strong correlations is with the gas phase turbulence, also measured in the ionized gas and in the molecular gas. So in both of these, we see actually a very clear correlation emerge, suggesting the strong link between the turbulence in the gas phase and the ability of that galaxy disk to well mix their metals, right? So all of the things with high turbulence have the most homogeneity, are the best, most well mixed. So this is all looking at the matter cycle in galaxies, but at sort of these 100 parsec scales where we can measure individual H2 regions and isolate them from each other. I'm glossing over a lot of the physics and our ability to actually make these measurements very precisely, which rely on an understanding of actually the detailed nebular structure, in particular some of our assumptions about the temperature structure, the density structure in the gas that go into our measurements of all of these characteristics. So to try to address that, within SDSS, Sloan Digital Sky Survey in its 5th incarnation, we've built a new telescope as part of one of the new projects called the Local Volume Mapper. So the idea here is while things like MANGA were doing kiloparsec scale surveys with thousands of galaxies, FANGS is doing sort of 50 to 100 parsec scales on 100 galaxies. LVM aims in the local group to do something like 1 to 10 parsec scales to really chart out the resolved internal structure of nebula and understand more of the core of the physics related to these nebulae. And so to achieve this goal, we've built a completely new telescope that uses 3 DESI spectrographs fed by 1,800 fibers. These have about an R of 4,000. And because local group targets are large on the sky, we actually only need something like 40 arcsecond spaxels. So these are 16 centimeter telescopes that we have built that are surveying the sky at LCO now. So this is a project that we just recently commissioned and started survey operations in last November. Our ultimate survey footprint that we're planning is a large box along the Milky Way plane, all of the LMC and SMC, and then a large contiguous region across Orion. We'll also do an all-sky grid and do some individual targeted local group and local volume galaxies. But to cover such a wide area in the sky, that means we really need a large footprint for our IFU, for our optical integral field spectrograph that we've built. So each footprint with LVM is almost the size of the full moon. So this seems very, very large, of course, but if you're studying Milky Way targets like, for example, the Rosette Nebula, this is in actuality how big it is compared to the size of the full moon. These things are very, very big on the sky. You need a very large field of view to efficiently survey these objects. All right, so we've started survey operations in November, as I said. One of our highest priority targets was Orion. And so you can see here the constellation of Orion, right? This is the Hunter. And you'll see, of course, these stars are the ones you'll see by eye. Here in red, this is a H-alpha outer ring on the bubble. And in yellow, something you wouldn't see by eye, this is the molecular clouds associated with the Orion Nebula. And so I'm going to show you our initial LVM data from this central region here. This sits slightly above M42. This is sort of the Orion Nebula that you are probably commonly seeing in photos. So we're going to zoom in on this region here and see our view, glimpse into the Orion coverage that we have. So in pink, we're seeing the H-alpha emission that's filling this big cavity and associated with this compact flame nebula. You can see low ionization sulfur-2 emission more towards the outskirts, and high ionization sulfur-3 emission in magenta here in the center. This is the Horsehead Nebula here. You can see these cometary globules that are being eroded, and all of this is carving out a space inside of the dust-rich, 12-micron PAH-rich emission that you're seeing on the outskirts here. So if we transform this into just the H-alpha view and zoom in a little bit, because this is Orion, our nearest, best studied star forming region, you can see how we can start to directly relate all of these ionizing sources, these O stars in particular in dark blue, with a number of these nebula. And we can also try to track how the B stars may or may not be contributing to this ionization across the region. And so with these sorts of data, we can start to play the game of building up our understanding of how the physics of the stars is interacting with these interfaces with the dense molecular gas. The Orion B molecular cloud is sitting over here, so you're seeing directly these interfaces between the stars and the gas where these ionized emission lines are telling you a lot about the physics of these feedback processes. So within our survey, we of course will cover a large area of the plane, but some of the initial regions, particularly that people in my group are studying, is M20, which is a nice little compact, picture-perfect single star H2 region, where we see actually very uniform temperature structures, but inhomogeneities in the density structure. We see these sort of clumps that are still remaining in the nebula. So that's being studied by my PhD student, Natasha Sattler. And then Eduardo Mendez Delgado has been looking at Orion, where this is LVM data. We're already starting to be able to map out in amazing detail the abundances of all of the typical sort of elements you look at, oxygen, nitrogen, sulfur, but also things like iron and recombination lines, as well as collisionally excited lines across this nebula. The LMC is another one of our core targets, so this is our coverage to date. This is N44 here, and 30 Doradus is over here, so we're just starting to get to that. And so my postdoc, Ksenia Egorova, has been tracking our progress here and starting to work on a paper. And finally, we're going to cover a sample of sort of local group, local volume targets where you don't have to get very far away for our 40 arc-second spaxels to get to very large physical scales. But this can actually be very well matched to things like Euclid, where you get amazing detail on all of the stars in this galaxy and can map them to these ionized structures. So I have shown you the metallicity variations we're starting to map across galaxies and how we can see how this is mixed by turbulence. And I've also shown you how we're building from these resolved, even parsec scale maps to integrated galaxies. Thank you.
Questions for Catherine?
I'm wondering how could we understand the sigma metal be slightly more correlated with sigma CO than sigma H alpha?
Yeah, so my expectation is that the CO is tracing a thinner layer in the plane than the H alpha is necessarily. Much of the H alpha is actually probably reflecting the diffuse ionized gas structure, which is on larger scale heights and may be less directly related to sort of the thinner disk where the star formation is happening.
My second short question is, how about instead of looking at correlation with star formation rate, but instead of looking at correlation with sigma star formation rate? That means we subtract the radial dependence. And
right. Yes, so far we've focused on doing this in a global sense, but I think there's a lot of power to breaking this up radially, potentially, or to smaller sort of kiloparsec regions to look at this, but we haven't done that yet. Yeah.
Thank you. It's maybe somehow connected. Regarding the metallicity variation and the dispersion in the metallicity, how does the alpha enhancement, so star formation timescales, for example, how is this factoring, or how much that could be a factor to explain or can you exclude that the variation that you see in metallicity can be due to alpha enhancement?
I think, so these are all measurements done in massive star-forming galaxies with long extended star formation histories. So I suspect that anything tied to shorter-term variations would be swamped by sort of those long-term signatures. I haven't thought about this question in detail, but we can talk about that more.
One last question, maybe?
Thanks a lot, Kathy. I was wondering, can you measure velocity and velocity dispersion and connect it to metallicity and feedback using the LVM
Yeah, with
data?
LVM. Yeah, so the spectral resolution is a bit better than MUSE, but it's a factor of 2 better. So we are trying to do things like map the abundance distribution in, do I have it? In things like Wolf-Rayet bubbles. So this is work that my postdoc Oleg Egorov has been working on. And so here we're trying to chart out, if those winds are, if we're really seeing evidence of enrichment associated with those winds, and there we can actually track the bubble expansion velocities from the data that we have. And so far it looks like things are relatively homogeneous within this bubble, but the data reduction pipeline, we're still getting some tweaks out, especially on the kinematic side. But I think that this will be an interesting question to address. Yeah.
Thanks.
Okay, let's thank our speaker again. And the last talk before the poster session is given by Peter Watson. And he will talk about star formation in intermediate redshift clusters as seen by James Webb.
Okay. So, this is my talk. I'm Peter. I work at ENAV Padova, and I'm going to talk about star formation in these clusters, mostly with JWST NIRISS. So it occurred to me that actually NIRISS is probably one of the least used instruments at this particular conference, so I'd give a very brief overview of what it is. It's technically a combination of two things in one box. It's the fine guidance sensor for the entire telescope, fixing the pointing and so on, and it's the near-infrared imager and slitless spectrograph. It's got an interesting history. It was originally built as quite a different instrument, and then for various problems with the cryogenic calibration, in the space of about 1 year, it was turned into the instrument we now know as NIRISS, with 4 separate observing modes: single object slitless spectroscopy, aperture masking interferometry, which are both generally for transiting exoplanets, and the 2 which are most relevant to this talk are wide field slitless spectroscopy and broadband imaging. So, broadband imaging, it's a single 2.2 arc-minute square detector, so quite large. It's got larger pixels than NIRCam, for those of you who are familiar with that, which actually makes it slightly more sensitive to low surface brightness galaxies. And a lot of the filters were originally NIRCam filters, and they're spares, and they were reused for NIRISS itself. Collective wavelength coverage over all of these filters is around 0.8 to 5 microns, obviously not all at the same time. And the second mode, one which I love, is wide field slitless spectroscopy. So very low resolution spectroscopy over the entire field of view of the detector. Detector size, for those of you more familiar with MUSE, it's about 4 times the area. It makes it extremely useful and efficient for a quick redshift search over a large area. If you've got bright emission lines in this particular wavelength range, you'll see them with NIRISS. And it's actually got 2 orthogonal filters. If you think about the way that the spectra are dispersed, you need 2 of them in a crowded field to actually properly distinguish objects. There's a nice little illustrative diagram on the right there. That's not quite what the output looks like. To show you an example, this is roughly the field of view and output of NIRISS. Yes, it's complicated. You can talk to me about the reduction if you want, but that's generally what we deal with. And that's the Abel 2744 cluster on the left, for those of you who are familiar with that. Now, the science we originally intended to do was looking for Paschen lines in ram pressure strip systems. So Paschen lines are another hydrogen line. Paschen beta in particular is one we're interested in. Rest frame 1.2 microns. Good indicator of star formation, insensitive to gas temperature and density, and compared to the Balmer lines, it's significantly less affected by interstellar dust extinction. So the original aim was to try and identify obscured regions of star formation, and secondarily, an additional measurement of dust extinction where we have one to compare to already. So, Abel 2744 has actually already been shown a couple of times, I think. It looks pretty, and I'm showing here the existing Muse data cube, ones that we have from Alessia and others. And there's the nearest footprint in orange as well. So the Muse data cube was 4 pointings making that mosaic. That's just one single pointing with nearest. It's quite a large area, and there's quite a good overlap. So we try to focus on the RAM pressure stripped galaxies previously identified. It's located there in the cluster, and that's what they look like more zoomed in. The reason we're looking for these is, there's already a lot of data on them. We know there's very long H-alpha tails, and we want to see, this should mean that we're able to see some Paschen beta lines. To cut the reduction out, this is what the spectra look like from Nearis. Unfortunately, it turns out that Paschen beta is right on the edge of the sensitivity in this filter. So there are two potential detections. There's the top left and the bottom left. The rest of them are unfortunately a little too contaminated or noisy, or just straight up out of the wavelength range. Unfortunately, and again, on close inspection for the top left galaxy, it turns out that this is not Paschen beta. It's just a contaminated galaxy which just happens to coincide perfectly with that wavelength. The reason we know this is because Paschen beta, sort of left to right, is the combination of the spectrum and the position. Now, if it were a actual spectral peak, we should see a single peak. Instead, we see a dispersed line on the right-hand side. So unfortunately, that just looks like a problem with the contamination modelling. Very annoying, false positive. That leaves us with one detection of Paschen beta. We can, however, obtain a sort of spatially resolved map. It looks like this compared to H-alpha. So we do find some spatial extent of Paschen beta. It's remarkably concentrated in the centre, but because of the way the sensitivity works, I'm not going to stake anything on this being more than just the spectra being cut off, which I want to stress, this is not a nearest problem, this is just a wavelength and filter alignment thing. But we do at least find one. And to prove that it's not all just in my head, at higher redshift in other parts of the field, we do manage to extract the lines as well. There's H-alphas, Paschen beta, and a whole bunch of others. So it exists, it's real. So instead, I'm going to pivot a little bit to talking about another galaxy in Nearis, but not in the Muse field of view. And the reason for that is that as I said, this is a very nice image. Someone's already mentioned that we have the Uncover and Mega Science proposals. Along with HST, this means in this field of view, roughly there are 36 photometric filters, which is a ridiculous amount of constraints. So, we want to have a look at this galaxy. What can we find out about it? Can we infer the star formation history without having dedicated spectroscopy? Trouble is with this sort of resolution is we have to identify all of the interlopers in the field, anything that's in the field of view, coinciding on sky, but actually at different redshifts. It's a curse and blessing of high-resolution, high-sensitivity observations. Showing the example on the right, in actual fact, every object apart from the sort of bluish point in the middle is an interloper. All of these other galaxies are either foreground or background. So we have Nearis, we can infer some spectra, we can find a redshift from those, and we also have bagpipes and a lot of photometry to work out the rest. So, focusing on this galaxy, F0083, first identified by Matt Owers in 2012. That's what it looks like. On the bottom there, I'm showing what appears to be a redshift 3 interloper. On the top, sort of bagpipes fit, showing that various parts of this are actually at other redshifts, 0.5. Sorry, should have said, cluster redshift itself is 0.3. So anything not on that redshift we can disregard. Interestingly, there are a couple of objects which are perfectly coincident with this redshift. Showing this one here, with a stellar mass probably of about 8.6, plus or minus 0.1. Mass-weighted age of around 6 gig-years. I've shown there 2 fits from bagpipes using different methods, one with sort of double exponential, and one with sort of integrated bins star formation history. So that's interesting. This is at the same redshift as the galaxy itself. Now, if we cut this very interesting galaxy into separate components, we can try and fit the mass-weighted ages using bagpipes, and we end up with something more like this, sort of masking out other bits of the galaxy which aren't fit very well. And we find this small elliptical galaxy is at a much older than the rest of it, and that this mass-weighted age decreases along this tidal stream there. Showing this more clearly, these three separate components formed one after the other, going from sort of around about mass-weighted age of 4-ish gigayears down to about 1 gigayear. Now, we don't have to cut it into components like this. We could also do a roughly pixel-based SED fitting, and so I did. So we have star formation rate maps, and interestingly also, stellar mass distribution. It's very clear. Almost all of the mass of this galaxy is smooth and contained in the center. What looks on the left in the photometry, like sort of stripped components, contains less than 2% of the entire mass of the galaxy. And you can really see here this separate elliptical on the bottom left. That's a completely distinct object. We do get NIRIS out of this. We actually have sulfur-3 and helium-1 emission lines, all concentrated on the leading edge of the galaxy, seeming to indicate sort of shock heating from the ISM interaction. So, putting all the bits together quickly, because I think I'm running out of time, what we think happened. Most likely, this is an interacting system between this small object on the left and the spiral arm back when it was in a different position. The galaxy spun round, producing this tidal stream stretched out, and then we have a much more recent burst of star formation triggered around 400 megayears ago, presumably when the galaxy and its companion fell into the cluster, and therefore it's been stripped. So, to sum up in conclusion, as I said, most likely ram pressure stripped, we can infer from photometry, consistent with a small minor interaction that later falls into the cluster, and it is quite a rare example of presumably both of these happening at the same time and visible. And also to say, NIRIS is very, very useful. Unfortunately, it wasn't for Passion Beta, but we do have a lot of other great science out of it. Thank you.
Thank you. Questions for Peter?
Thanks for the interesting talk. So, I'm here, yeah.
Yep.
So if you look at like right-hand side of this interesting galaxy, you see very diffuse stellar components. And I realized that in my paper, I referred this as ultra-diffuse galaxies. So do you think that could be a companion of this very like fascinating galaxy cluster?
Do you mean this component?
Yeah, that one, yeah.
The photometric fits I have put this at a slightly higher redshift than the central galaxy itself. I'd need to do a few more fits just to convince myself. The slight problem is there's this very bright component here, which is definitely higher redshift. If it is an ultra-diffuse galaxy at a similar redshift, it's almost certainly been stripped off, but I wouldn't like to speculate too much without being certain of the redshift.
Yeah, thank you.
One last question.
Hi. Do you have plans to expand the wavelength coverage of observation for this galaxy?
Yes, and I'm glad you asked. From archival data, there should also be UGMRT observations, and there's definitely Chandra X-ray observations in the soft and hard band. The bit I slightly skipped over is that there is also a CFER type 2 core for this galaxy. So if we look at the X-ray in the hard and soft band, we do see a difference between sort of central AGN X-ray emission and much more soft X-ray dominated tail. Presumably, I would guess as a result of stripping and ISM interactions.
Okay, so before moving to the poster session, let's thank Peter, but also all the speakers of the afternoon session as well.
So I invite the poster presenters just to come here in alphabetical order, and we will project your slides, and you can have your 2-minute highlights. And just as a note, this is just the first set of posters, and this poster will be up until Wednesday, I think, and then there will be new posters. So I encourage people just to check out these posters as soon as they can. No? Bianca? Bianca? Doesn't work. E non mi funziona.
Quando hai premuto presentazione, non va in presentazione.
Ma non si vedeva. Ecco. Però adesso dove vado per dargli...
Ma appena fai partire la presentazione.
ma non sono neanche riuscita ad arrivare fino a là. Lì si vede. Qui si vede.
Aspettiamo un attimo.
Ecco. E adesso però non so come fare.
Dov'è il mouse?
Adesso. Ok. No, fare su view. No, view, sinistra, destra, là. Il penultimo.
Poi aspetta un attimo, guardiamo un attimo qui. Se lo prende? No. Dov'è?
È che bisogna andare col mouse di là, penso, perché il secondo schermo è con l'altro mouse.
È andato, è ritornato di qua?
No, perché?
Perché è sul doppio schermo.
Okay. Is this the first one?
It's the third one. That's okay.
Okay. So here is this, and you have 2 minutes.
Okay.
I think it's...
Let me know when I... Okay. Good afternoon, everyone. My name is Ayan Acharya. As of this month, I am a postdoc at ENAF Padua, working with Benedetta Vulcani. You might have seen that my badge actually says Johns Hopkins University. If you met me at the conference last year at Johns Hopkins University, I was wearing a badge that said ENAF. So I clearly like keeping people confused. Anyway, today my poster is about the work that I did when I was at Johns Hopkins University working with the Foggy group, Foggy Simulations group on metallicity gradients. I don't have to explain what metallicity gradients are, but this is our current understanding of the evolution of metallicity gradients. This is the current state of the art. The hex bins are the observations, and oh, this is not the current state of the art. I will...
To do. E non so cosa fare. Ecco. Il tuo? Sì, ma...
I'll scroll. That's okay. That's fine, no, that's okay. That's okay. Let's see, does this help?
No, I think that
No. No. Oh shit, yeah, you're right. No, I can't scroll. Maybe I should do escape, yeah.
Aspetta, facciamo così. Ma alcuni non si vedono perché sono... Sorry. The problem is they have different sizes, so if you don't go slideshow... Okay.
Okay, this is fine. Right, and Okay. It does not like my slides. You know what I'll do? I will just drag this, make it bigger. Oh, this is the other way around. Okay. Thank you. Oh yeah. Perfect. Does it change? Yes, it does. All right. Thank you for whoever that was. All right, anyway, as I was saying, this is our current state of the understanding of evolution of metallicity gradients, observations, and the hex bins. Several state-of-the-art simulations in the various colored patches, including the foggy simulations in the pink shaded region. Two big takeaways, which you have already by now. Okay, I will not do full screen this time. This is fine. I'm happy with this. Is that okay? All right. Two takeaways from this massive mess of a plot, which makes the upcoming and also current observations with JWST of metallicity gradients very challenging. Number one, there is significant scatter and short timescale variation in the evolution of metallicity gradients, as seen in the foggy simulations, which is the very sharp wiggly lines in the pink region. And number two, which is very apparent, that, okay, should I just keep my cursor here? All right, I'll go ahead. The second conclusion is that, as you can see, there is almost no positive gradient seen in any of the simulations, unlike in the observations. Many observations are positive. This poses a tough challenge to the interpretation of gradients. Now, what can we do about it? We propose a complementary method of quantifying the spatial distribution of metallicity, which also ties to the stellar feedback in the galaxy. Now, does that actually help? Does this new approach help us understand the evolution in a less crazy way? To understand that, you have to please check out my poster, which is a big black one right at the very end of this row, or look up the paper we recently submitted. But I just want to finish by saying that although this is the work that I did in my previous position, I am very excited and looking forward to starting working with the JWST passage team, which has the nearest data, and continue to do study these amazingly spatially resolved ionized gas properties. But thank you. That was way more than 2 minutes. Not my fault.
Hi everybody, my name is Cecilia Bacchini. I am a Dark Fellow at the University of Copenhagen, today I will present the work that I did when I was working in the GASP collaboration as a postdoc in Padova. So in my poster I present this work about the 3D modeling of the molecular gas kinematics in optically selected jellyfish galaxies. These are 4 star-forming galaxies in clusters that are part of the gas sample, but so they have Muse data cubes, but also in these cases CO120 data cubes taken with ALMA. These galaxies host AGNs and they show ionized gas outflows. And they also show these beautiful tails of ionized and atomic gas due to run pressure stripping. From the map of the CO emission, this system show clearly some disturbed morphology and disturbed also and the signs of compression in other cases than this galaxy due to the action of run pressure. And from the velocity field you also see that the kinematics of the molecular gas is very perturbed in these systems. So to understand what is going on in these galaxies, what I did was to use the software 3D Barolo to model the CO data cubes and extract the kinematics of the molecular gas. And then I also modeled the stellar velocity field to extract the stellar rotation curve, and by comparing the molecular gas and the stellar kinematics, What we could understand is that there is some of these systems show kinematic lopsidedness that is likely due to the effect to the action of run pressure. But we also find that the CO is more resilient to run pressure than diffuse gas phases. And indeed, the gas kinematics is dominated by rotation, the classical rotation, or by radial motions due to the presence of stellar bars, this in the inner disk. In the outskirts, instead, we find indications of radial motions due to the action of run pressure. We also find indications of strong turbulence that may be enhanced by the action of run pressure. And then interestingly, we do not find any clear indication of CO outflows, which indicates that AGN do not drive always multi-phase AGN outflows. So if you want to know more about this, come to my poster.
Good evening, everyone. I'm Laura Di Federico. I'm a PhD student at Munich University Observatory, and my current work relies on improving the cooling module in the cosmological code OpenGadget 3. Today, I want to talk to you about the results I carried out in my master thesis at University of Bologna, supervised by Franco Vazza and Fabrizio Briganti. I've analyzed a set of highly resolved cosmological simulation of a galaxy cluster which was obtained through ENSO code. The motion of the gas in the cluster depends on several factors such as turbulence, accretion, merger, shocks, gravity, and in particularly on a central AGN. The AGN has been resimulated 5 different times by varying its power. Having this set of simulations, we wanted to investigate the kinematics of electrons injected into the intracluster medium and analyze the observable properties of emerged X-ray cavities. And we wanted to use both approaches in order to get an estimate of the AGN power. So I just give you 2 examples. Using the particle kinematics, I found a set of relation for different instant of times after the injection of the particles in the cluster, able to link the distance reached by the particles to the power of the AGN. And in order to obtain an estimate of the AGN power through the analysis of the observable properties of the X-ray cavities, we have to make a ratio between the energetics of these objects and their ages. But in literature, there are very different methods in order to get this quantity. So we wanted to analyze which is the best method to obtain this quantity, because of course it affects a lot the estimates of the power. So in this case, you have to imagine that we have one cavity which evolves over the time. The true age is the gray line. And for 5 different instant of times that are basically 5 snapshots, I tried to estimate the age using different methods. If you want to know more, please come to my poster and ask me.
Hello everyone, my name's Jacob Elford. I'm a final year PhD student at Cardiff University. So I've been studying the circumnuclear regions of the wisdom sample of nearby galaxies to try and understand the connection between this circumnuclear region and the AGN activity. So we looked to see if there's a correlation between, We looked to see if there was a correlation between the circumnuclear molecular gas mass and the AGN activity, but we found no correlation. So, this should suggest that the circumnuclear regions in our sample of galaxies are not fueling the AGN. Okay, so if the AGN are not being fueled by the circumnuclear gas, can they still impact the circumnuclear gas through AGN feedback? So we looked at this through the molecular gas concentration, and we find that we have a variety of molecular gas concentrations, which differs from previous results. So this could either be that the molecular gas concentration is set by secular processes, or we are seeing maybe a turnover point in this relation, because other previous works have found that when you get to higher AGN luminosity, the molecular gas concentration tends to fall off. So it's almost like the AGN is outflowing and pushing gas and causing deficits in the molecular gas concentration. Finally, we studied the nuclear millimeter luminosity in our sample. Ooh, that's right, no worries. And we studied the nuclear millimeter luminosity in our sample of galaxies, and we found it correlated well with the supermassive black hole mass as well, sort of in between here. This would be the sort of the correlation between the molecular gas concentration. This is the previously found relation, and then the blue points are our points. So then we found this correlation between the supermassive black hole mass, the nuclear millimeter luminosity, and the X-ray luminosity from the AGN. So this could have important implications for the AGN accretion process, because we find that radiatively inefficient processes can describe this new fundamental plane. So for further details, please see my poster, and if you have any questions, feel free to ask me. Thank you.
Because they're all different sizes, of course. Is that okay? No, let's go. Okay. I don't feel brave enough.
Okay. Hi everybody, I'm Anna Feltre from the Observatory of Arcetri. So the image you see on the right is actually an extract of 24 muse pointing of along the major axis of M33. So with this data we can actually map the emission from the ionized gas of M33 with an unparalleled resolution of 4 parsec. So you can see the emission of the ionized gas, as illustration, there is H alpha in red, O3 in blue, and S2 in green. Most of these nebula are basically H2 region ionized by Wolf-Rayet star or OB stars. But we also have some supernova remnants, planetary nebula, as well we can study the emission from the diffuse ionized gas. So there is actually a wide variety of studies that you can do with these data sets. We can link the emission line properties with the energy sources of feedback. We can characterize these energy sources as well the physical condition of the ionized gas of H2 regions. But most importantly, we actually can resolve the internal structure of H2 region with a very high resolution. So we can study the impact of the diffuse ionized gas on the integrated spectra of this H2 region. We can study their nebular geometry as well as the escape fraction of ionizing radiation. So we do all of this by combining our MUSE datasets with multi-wavelength band available, as well as exploiting tools as new generation photoionization models and machine learning techniques based on neural networks. So more details are in the poster, and thank you.
Hello everyone, my name is Silvio Fortuné and I study galaxy evolution with a focus on quenching and rejuvenation. I do that by tracing galaxies through the Magneticum Pathfinder cosmological simulations and see how they compare to the star-forming main sequence. So here we see 4 galaxies that start on the main sequence. The cyan one stays on it, while 3 of them quench below. The magenta galaxy makes it back onto the main sequence, while the blue galaxy actually only quenches slightly below and then keeps a constant star formation rate until the main sequence itself declines down to it. So I classify the galaxies according to those formation scenarios and want to find out what shapes those scenarios. So in this case, I follow the median accretion rates across cosmic time of the 4 classes. And here we see the accretion rates onto the virid radii of the galactic halos. And we see that all the accretion rates kind of scatter around similar values down to low redshifts, while the main sequence type galaxies stay at the highest accretion rates onto the halo. However, if we divide the accretion rates onto the galaxies and the centers of halos by the accretion rates at the virid radii, we see that the magenta rejuvenating galaxies and the blue rejuvenating galaxies tend to higher values than the quenching galaxies, but also the main sequence type galaxies, which is an indicator for a rejuvenation that is fueled by a fountain process. And if I manage to spark some interest, and if you want to see more results about those 4 classes, I invite you to have a glance at my poster and look forward to a publication that is expected in the near future. Thank you very much.
Hi everyone, I'm Nadine Hank. I'm a PhD student at the Captain Astronomical Institute working with Mark Verheyen and Sarah Blythe. So the physical processes and environmental conditions that drive galaxy evolution over cosmic time can often result in asymmetries in a galaxy's gas and stellar distributions. The H1 disks of galaxies are particularly sensitive to these processes because they are relatively fragile and diffuse, and they typically extend beyond the stellar disks. However, because of the susceptibility of H1 to being disturbed by both external gravitational and hydrodynamical forces, as well as internal secular processes, makes it difficult to identify which process may be a primary driver for the asymmetries that we observe. So in this study, we focus on galaxy interactions and mergers as a possible driver for these drivers of asymmetries, and we turn to simulations where we're able to trace a galaxy's dynamical history and also obtain a large sample of spatially resolved samples. So we construct about more than 1,000 mock H1 data cubes and extract their global profiles and morphological and their moment maps to calculate spectral and morphological asymmetries. And we also design these data cubes to match the Apatite medium deep H1 survey. And so one key result that we find is that galaxy mergers and interactions to a lesser extent are likely the dominant processes responsible for the observed asymmetries. And this isn't trivial because there is some conflicting results in the literature on whether or not galaxy mergers do lead to asymmetries. But for more results, you can look at my poster. Thank you.
Hi, I'm Ziwa Ho. I'm an undergrad from National Tsinghua University and HI in Taiwan, and I'm working with Liquid Lens Group. So my research is about comparing different definition of quenching area with manga pipe 3D pipeline and with MPLO 11 version. So the definition of a quenching area is various, and there is no exact or absolute definition yet. And it brings some benefits, but it also causes some concerns. It may lead to contradictory results or conclusion, or it will be a problem if we want to do the cross verification. So we consider 4 iconic definitions of the quenching area, and each of them has a tight or loose relationship between star formation. And in the maps in the lower panel, they show the spatial distribution of the quenching area in different definitions. And as you can see, some of them look similar, but they are actually not consistent in all definitions. So to be more specific, we use 2 parameters to classify the galaxy quenching mode as inside or outside, corresponding to the star formation shuts down from the center or the outskirts of the galaxies. One parameter is FQ, the fraction of the quenching area. In the other parameter is CQ, the concentration of the quenching area. And the result is also shown in the lower panel. And as you can see, the result is very different in different definitions. And we are still working on the interpretation of these results. If you are interested in this topic, my poster is in the back, and you are very welcome to discuss with me. Thank you.
Hello everyone, my name is Ryota Ikeda. I'm a PhD student at NLJ. So in this poster, I'm presenting the results from the crystal survey which is an ALMA Cycle 8 large program. So this survey aims to spatially resolve the star-forming galaxies from redshift 4 to redshift 6 in both C29 and dust continuum emissions down to a kiloparsec scale. So on the left, you can see some of the examples of the dust continuum emission, which already presented in Mitsuhashi et al. On arXiv. And on the right, you can see some of the C29 contours overlaid on the HST images. And you can see that we are looking at the galaxies in various merger stages. So we measure the sizes of C29 and compare with the sizes of the continuum emissions in restream UV and far infrared, and we find that C29 is more spatially extended. And as I show on the right-hand side, we discuss what is the origin of the extended C29 emission, because the spatially extended C29 emission simply indicates that those extended C29 at larger radii cannot be explained by photodissociation regions alone. So please come to my poster for the discussion we did in this study. Oh, sorry. Sorry, I'm not done yet. So yeah, finally we present some of the correlations between C29 and dust and Lyman alpha properties and try to explain what is the reason for those correlations. So again, please come to my poster. And aside from this study, I'm also working on different topics, including the spatially resolved multi-CO line emissions, CO221 line and 524 line in cluster galaxies at redshift 1.5, and also the ultra-diffuse galaxies seen in JWST. So I'm also willing to discuss these topics. So please come, please feel free to talk to me. Thank you.
Hi everyone, I'm Kirtana Jagadeesan and I'm based in Chile at Universidad Diego Portales. So today I'd like to talk to you quickly about a project called Budimanga, a spectroscopic survey of galaxy bulges and disks. So today it's been a recurring theme, so we're well aware that galaxies come in a wide range of physical properties and structures, and these properties are again shaped by a similarly wide range of physical properties. This can vary from internal evolution of galaxies through continuous star formation or through environmental effects that can change and alter a galaxy's structure and morphology. So these physical processes are known to leave behind characteristic signatures on different regions of a galaxy, different parts of a galaxy, especially the major components of a galaxy, which are the bulge and the disk. So with Budimanga, we've built a sample of bulge and disk spectra by using IF integral field spectroscopy combined with a novel technique, a novel code called BUDDY, which essentially models each image slice of a galaxy. Well, it models the bulge and the disk components in each image slice of a galaxy in the multiple wavelengths of an IFU data cube. So from there, we can then extract the clean bulge and disk spectra. So this Budimanga sample is by far the largest sample of such bulge and disk spectra to date. And the sample also covers it covers a wide range of morphology from ellipticals to spiral galaxies, and I'm focusing on spiral galaxies in this project. So essentially with the spectra, we perform full spectral fitting, extract the stellar populations of the bulges and disks, and reconstruct the mass assembly histories of these components. From there, we can try and constrain the different formation scenarios that we see in spiral galaxies. So if this interests you, my poster is right there, so please come talk to me. Thank you.
You want me? Yes.
Hi, I'm Amir. I'm part of the well-known story GASP team.
and now I'm PhD students in Bologna. We worked on the gas metallicity of the jellyfish galaxies, ramp pressure sweep galaxies. We had two intentions. First, to see that how the enrichment processes go on in the tail of those ramp pressure sweep galaxies, and then how it goes on even within the disk. So we started from the two close clusters that we have in the Muse GTO program. And we selected 12 ramp pressure sweeping galaxies out of those two clusters at the redshift 0.3.4. Sorry, my allergy kicked in. That's the melon from launch. So one of the highlights of this investigation is how the metallicity changes as we go through the central part of the galaxy to the end of the tail. And we see that for most cases, and for all cases with the high mass, 10 to 9.5, 9.7, we see that the metallicity decreases as we go to the end of the tail, which says that there is another enrichment processes going on in the tail. Also, we investigated the global metallicity values for those galaxies. We saw that they share the same metallicity, although that systematically the metallicity in the tail is lower than the metallicity in the disk. Another step to see that even how the disk is affected by the ramp pressure sweeping and how the metal content of the disk is affected, we went through all the 12 clusters, which is part of the Muse GTO program. We selected 21 ramp pressure sweeping galaxies, and in total 34 control cluster and control field galaxies. We see that obviously the metallicity in the ramp pressure sweeping disks are higher than the metallicity for the control sample with a given mass, which says that clearly that the whole process of the metal enrichment, yes, is totally different. Thank you. You have 4 ways to have more information. The poster as the well-located area, the paper which is published, wait a few months for the next paper, or talk to me. Thanks.
Hi, my name is Shalini Kurinji Vaindan, and I finished my undergraduate studies at Caltech, and now I'm doing a Fulbright Fellowship in Germany. I'm currently working at the Max Planck Institute for Astronomy, studying the role of the environment and AGN in galaxy evolution. And in particular, I'm using the cosmological simulations, Illustris TNG, which are a powerful tool for analyzing populations of galaxies at higher stellar masses, earlier cosmic times, and also in the densest cluster environments. And so first, I have looked at early massive galaxies. In the simulations, we find that there is a non-negligible fraction of massive galaxies which are quenched above redshift 3. And the question is, what suppresses their star formation so early in cosmic time? Well, in the simulations, these galaxies have resided in more massive host halos during their lifetime. And as a result, the large-scale environment can mildly contribute to the growth and activity of their central supermassive black holes. And we find a strong correlation between the onset of AGN feedback and quiescence. And I did this work with Michaela Hirschman at EPFL. And now, I am working on studying local satellite galaxies in Annalisa Pilipich's team, specifically jellyfish galaxies in the Illustris TNG universe. Here we're also interested in whether there is a link between environmental effects and AGN feedback. In the simulations, we find that jellyfish galaxies have higher AGN fractions than central galaxies and other satellites. But I would be very happy to talk more about it at my poster. Thank you.
Yeah. It's okay. We make it very big. Mike Barlow.
Hi, everybody. My name's Kamlal or Forsyth. I'm a PhD student working at the University of Waterloo. with Michael Ballo. So in this work, these are basically just the results. In my work here, I've looked at understanding the morphological evolution of quenched galaxies in the illustrious TNG 50 simulation, which was just nicely introduced. So basically, using a set of morphological metrics, we can distinguish different quenching signatures or quenching pathways, whether that be galaxies that are quenching inside out or outside in, additionally separating them from star-forming galaxies. Moving past that, using a machine learning model, we can separate these different populations very cleanly in this morphological parameter space, and then also move to regions where the purity is very high or the completeness is very high. But you're going to have to make trade-offs in either capacity. If you have any other questions, you can certainly come look at my poster. The main goal of this, right, is to try to understand this space, especially when looking at real surveys of galaxies, not just simulated galaxies. Thanks.
Hi, my name is Neven Tomicic from the University of Zagreb. As a GASP member, I am working on deriving the diffuse ionized gas across the tails and disks of gas-stripped galaxies and jellyfish galaxies. Once when done, I separated areas which are dominated by the H2 regions from those dominated by the diffuse ionized gas. Among many results, the interesting one is that the source of ionization of the diffuse dominated areas are probably coming not from the young stars in star-forming regions, but rather from probably mixing of the interstellar and intercluster medium. Furthermore, I checked if star formation rates derived from H alpha or UV tracers are similar or different in those regions, and I found that the tails and disks shows similar results, but there is bigger difference actually between the DIG dominated regions from H2 dominated regions. For details and discussions, ask me at the poster. Thank you.
Hello, I'm Anna Velichka from the Geneva Observatory. So in the previous work, we derived abundances of some elements in the interstellar medium of a set of galaxies, distant galaxies. And these results are published. You can find the paper via the QR code. The main result we derived is for alpha elements over iron versus metallicity. Since our galaxies don't have measurements of masses, we use velocity width of absorption lines as a proxy for galactic mass, and the main result we derived is the subsample of high delta V90 galaxies show the high alpha Ni at higher metallicity. And then in the current project, we analyze some properties of model galaxies simulated by Yves Riva and Pascal Jablonka. First of all, we want to constrain masses of our galaxies. To do that, I overplot abundances of magnesium over iron that I got from the simulations and from simulated galaxies with different masses. And you can see that the simulated data show the trend in metallicity. More massive galaxies evolve faster to higher metallicity, which leads to the high alpha Ni located at higher metallicity. And the observed galaxies in our sample are consistent with star masses, roughly in the range of 10 to the 6, 10 to the 7 solar masses in case of low delta V90 sample, and 10 to the 9, 10 to the 8, 10 to the 9 in case of high delta V90 subsample. Then we test efficiency of feedback
of supernovae feedback, and we constrain velocity width as a measure of galactic masses. So for more information, you can come to my poster.
So thanks all the speakers. I'm really sorry for the delay of my laptop. Thanks all. Oh, I don't know. So thanks everybody for joining today, and see you tomorrow at 9 a.m. Thanks.